If you are in the second year of IB, you have 24 days to prepare for your first math paper, 25 days to prepare your second math paper, and 29 days to prepare for your third math paper. I am a university mathematician researcher at the University of Oulu, and I am the founder of Manifold Solutions, a mathematics-based company that helps industry to solve mathematical problems. And I'm here to help you with IB exams and get you inspired and see the beauty of mathematics. Okay, someone asked me to make an AI paper question. So this is applications and interpretations, old paper 1 question. I think this is standard level. So here we have someone very smart who deposits $1,000 into her bank account with an annual interest rate of 4% compounded monthly. So the annual rate is 4%, but it's compounded every month, so we will have to figure out what's the monthly compounding rate. Okay, so at the end of January and at the end of every month after that, she deposits $100 more into the same account. And we have to calculate how much money there is at the start of 2024, so that's in 2 years, which is 24 months. And then, on the other hand, we have to find how many months it takes to reach a certain number, which is 5,000 in this case. So what I would do, what I'm thinking the first thing when I see this, is that we would have to come up with a formula. I'll just denote it by F, well, F for formula, of the Fn. So how much money is there after n months? So let's say this is the amount of money of dollars at the end of the nth month. And the reason we should find this formula is because once we find it, then the answer to A is going to be simply F24. So because that's after 24 months. And the end of 2023, like the amount of money is the same in the end of 24th month and in the beginning of 25th month. So it doesn't matter which way around we do it. It's beginning of 25th or the end of 24th. But some of them will probably end up looking nicer in the solutions, but we'll see. Okay, so then B will be then solved by solving the inequality, which asks when is this formula going to be bigger than 5,000. Okay, so this is the setup, and this formula will depend on the parameters that we're given, which is the initial deposit, let's call it A, which is 1,000, and the addition every month, let's call it B, which is 100, and then there is some rate, some monthly rate, of which we know that in a year, so in 12 months, so if we compound it 12 times, so r to power 12, that should be 4% compounding, which means it's 1.04. So we know that r is the 12th root of 1.04. Now, a piece of advice. Let's not calculate this with a calculator just yet, because we're in the middle of the exercise. It doesn't make any sense to waste time on calculating this at this stage. In general, I recommend not using your calculator until the very end of the exercise for 2 reasons. Number one, it spends time. Number two, you might end up there is a lot of room for error if you do that, because once you calculate this with a calculator, you'll get a decimal number, you will have to round it, and when you use it in the later parts of the exercise, the rounding error can accumulate and get emphasized, and then it might influence your final answer. So unless you have a good reason to calculate something in the middle of an exercise with a calculator, I recommend not doing it. So let's leave it like this for a moment. All right, so using these parameters, we should be able to come up with the formula. So let me rearrange a little bit. Let me leave this part of the exercise only, and let me move my what I have written a bit upwards, like so. Put it here, maybe make it a bit smaller. Okay, so perfect. So let me try to write a formula for how much money is there after the nth month. So first of all, how many times has this initial deposit of 1,000, how many times has it compounded? It has compounded n times. So A times R to power n. Okay, so after the first month, it's been multiplied by 1 point whatever the monthly rate. After 2 months, it's multiplied it 2 times, so it's power 2, and so on and so forth. Additionally, at the end of nth month, we have added our monthly addition. Also, we have from the previous month, we have the monthly addition that we added 1 month ago. That has compounded once. So the one that we add just in the end of this nth month, that hasn't compounded at all. But the one that we added the previous month has compounded once, so we multiplied by R. And then we have the one that we added 2 months ago, the addition we added 2 months ago, and that has compounded 2 times, etc. Let me continue on the next line, etc. And what's the last term in this expression? It's the first time we ever added this addition is n minus 1 months ago, right? Because n months ago was the very first day, January 1st, and that's when we did not add the $100 addition. We started adding it only in the end of the first month, end of the second month. So in total, by the end of nth month, we have total n times made the addition. And so the last term is B times R to power n minus 1. We can think of this as RB times R. No, I'm sorry, this is not visible. We can think of this term as BR power 0. So this is how we see that there are n times this addition. Let me draw a picture. This is the first month. This is the second month, the third month, and the fourth month. Now, in the beginning of the first month, we have added 1,000, which is the A. In the end of the first month, which is the same as the beginning of the second month, we have added B. And then we have added B again, and we have added B again, and then at the end of this fourth month, we have added B again. So in the end of the fourth month, we have added B 4 times. And this B has by this time compounded 3 times. So this is why we have n minus 1 here. So if n is 4 in the picture, this B has compounded 1, 2, 3 times. Then this B has compounded 2 times, this b has compounded once, and this b we just added hasn't had time to compound at all, so it's just b, or b times r to the power 0, which is the same thing. Okay, and okay, let me just go back to our formula. But that's it, that's the formula. And what do we see? We see that this part is the sum of geometric series. I mean, I guess I could have actually just placed this I guess it would look better if I actually put it there. So nah, that's not good. Let's move stuff a bit. And so now we will fit it like so. Perfect. Now we see that this part is very familiar. It is, namely, the sum of a geometric series. Enter formula booklet. Ta-da! So what do we have in our formula booklet? Let's zoom in a bit. So here, the sum of n terms of a finite geometric sequence. Here we have the general term, which is in our case this. Oh, that's very interesting. I have like multiple cursors for some reason. Oh my goodness. Oh. Okay, doesn't matter. So in our case, U1 is B, right? Because they seem to start their sequences from n equals 1. So when n equals 1 is r to power n minus 1 is r power 0 is just 1. So our B is U1. Our n minus 1 is, our n is exactly this n. We can check it like this. If our n was 1, that means we would have just sequence of length 1. And here, if n is 1, then this sum will be just u1. You can check it by putting n equals 1. So then we see that this is also the sum of the sequence of length 1. So I always, because I have seen so many different formula booklets in my life which all use different conventions, so I have to always check that they the other option is to just derive the formulas yourself, so you don't have to rely on some formula booklet or something. But in this case, we want to rely on it. So when the number of these summands is n, in our case means from 0 to n minus 1, then we use this formula. Okay, very good. So in order to use this formula, let's just put it here, cropped out of the formula booklet. And now it's easy to copy it and use it. So in our case, this becomes, so let's copy the first term, and then comes the sum, which is in our case b times r to power n minus 1 divided by r minus 1. That's about it. That's it. So that's our formula. Now, so to answer A, I don't think we need to simplify this more, because we're going to just insert something in place of n, and then we will calculate it. So for part A of the exercise, we needed to substitute 24 in place of n. So let's first of all make a realization that r to power 24 is the same as just 1.04 power 2, because obviously, I mean, it's 2 years, so it's compounding this yearly compounding rate 2 times, but you can also see it from here that if you raise this to power 24, then 24 is 2 times 12, so 12th root of something to power 24 is the same as this to power 12 and then power 2, and now this 12th power cancels the root, so it's just this. Okay, very good. Now, using the calculator, for this you don't need any fancy properties of a calculator, it's just simple multiplication or power taking. So we have this equals 1.80816. So I just used the calculator. This is exact, so this is not this is not rounded. It actually ends at this. But here we have actually the r, which is the 12th root, so we can't escape it. So we have to calculate this actually. So this, also using some simple functions for calculator, so taking 12th root is the same thing as raising to the power 1 over 12. Let's make it bigger. Power 1/12. I have another video where I explain why taking a root is the same as this power, like that, but I'm not going to explain it now. Putting this into a calculator, so here's what we're going to put into the calculator. 1000 times this, because this we figured out, plus b times 104 power 2 minus 1. I'm sorry, b, of course, is 100. Divided by 12th root of this minus 1. And so I recommend putting all of this at once into the calculator. So the number I get is 3,574 .162. Now they asked us, I believe, to give the 2 decimal precision, because that makes sense when you're talking about dollars. So then that would be 3574.16. At this point, it's very useful to check that we are in the right order of magnitude, just to make sure we didn't go astray too bad. That's like one of the checkups that will help you to make sure you're on the right track. So though she's been adding 100 euros for 2 years approximately, right? So every month, so that means that she added 2,400 euros, plus she added 1,000 in the beginning. So that would be 3,400 in total she added. And then we know that it compounded by some reasonable rate. So yeah, it makes sense that it's a bit more than the amount of money that she actually added. It grew through the compounding, but didn't grow, didn't become like 10,000. So this looks like this is in the right ballpark, so we are not worried that we made some bad mistake. 3,574, so she basically increased her money by 174 euros, which is great if the inflation is not too bad. Okay, so now for the second part of the exercise, we have to solve the inequality, which is asking when is this greater than 5,000. So this inequality we gotta solve. So when you're so let's solve this inequality. Let me move stuff a little bit to the left just for now. So, and we need to solve n from this. We know a is 1,000. We know b it's 100. We know r it's this 12th root. So we know everything except n. And so we have to solve n. How do we solve n when it's in the power? Usually, like, the idea would be to bring this into a form where we have r to power n equals something, and then take the logarithm, and that's how we get n out of this. But let's see how can we simplify these expressions over here. We don't need this anymore. Okay, so I suppose I would just start moving things around like this. Let's multiply by r minus 1. We have a r power n times r minus 1 plus b r power n minus 1 is greater than 5,000 times r minus 1. Now, opening the brackets, we'll have a to power n plus 1 minus a to power r n plus b r n minus b is greater than 5,000 r minus 5,000. What I would do now, okay, let's move b to the left. So we have, and let's move b to the left. Let's see we'll have we can combine these terms so that we have r to power n, and then combine these terms so that we have r to power n a r minus a plus b, and then we move b to the right, so we have 5,000 r minus 5,000 plus b. Okay, notice that we know every term there. We know a is 1,000, b is 100, r is this 12th root of 1.04. So actually, I'm just checking that I did everything right. So we can divide by this term. So then we have that r to power n is 5,000 r minus 5,000 plus b, plus b is 100, so let's just write it. And then we have divided by, and let's put in a is 1,000 times r minus 1,000 plus 100. Now this we should calculate with a calculator, but not yet. Let's first take the logarithm. So now we have r to power n on the left side and something else on the right side. So let me move things a little bit. taking the logarithm, let's take just the 10 base 10 logarithm. So we'll have logarithm of r, and then the exponent comes here to that becomes a multiplier. So we'll get n times logarithm of r equals this thing. Let me copy it. Like so. And let's not forget to take the logarithm of the left hand side as well. So we'll have something like this. Oh, now it just looks like this numerator is 5 times bigger than the denominator, but it's not, because this is term 100. Otherwise we have, notice, we have 5,000, 1,000, 5,000, 1,000, but then we have 100 and 100, so it's not exactly 5 times bigger, so we can't really divide. Okay, so this is the expression. Let me move stuff a bit. So now what we have is that n equals the base 10 logarithm of this expression, which, well, to be honest, I shouldn't have opened these brackets. It's much easier to write so that it's 5,000 times r minus 1 plus 100, and then divided by 1,000 r minus 1 plus 100. Then times 1 over, let's make a straight line, 1 over log r. So this can be put into the calculator. Again, I recommend putting this all at once into the calculator, because you can write you can write formulas of this complexity into your calculator at once. If you start calculating one thing at a time, so first you calculate r, then you calculate what's r minus 1, then you multiply it by 5,000, you're running the risk of making errors, because when you I'll give you an example how this error could happen. So let me take my calculator. So the 12th root of 1.4 according to my calculator is 1.003273734, etc. Now, if I am not careful, I round it up here. I'm thinking, oh, I can round at 1, 2, 3, 4, 5th decimal, no problem. I went round it up. So it's going to be like this. Then I will plug it in here, and I multiplied by 5,000. But now when I multiply it by 5,000, what happens is that the rounding error grows 1,000 times. So so the correct answer, if I did not round it, my answer would be 516.368698, etc. But if I do this rounding, then then this would become 5016.35. So this is different already. So because even though I rounded this one at a very late stage, at like fifth, after the fifth decimal, because I have to multiply it by a big number, this error becomes visible in the final answer. I don't know what happens after taking logarithm, etc. Might not be visible, or it could be. In any case, you avoid these types of errors if you plug everything into the final formula and don't use your calculator before that at all, if possible. Okay, I trust you guys know how to put this all into your calculator, so I'm leaving this at this. Okay, but first let's fix a couple of things. So here we're supposed to have inequality, just as here. When we take the logarithm, the sign does not change because logarithm is monotonously increasing function, and when you apply an increasing function on the both sides of your inequality, then the sign stays the same. And when we divide by this logarithm, because r is greater than 1, the logarithm is positive, so when dividing by positive number, the sign still stays the same, like so. Another, by the way, simplifying thing is that here we can reduce by 100, so we can divide everything by 100, in which case 5,000 becomes 50, 1,000 becomes 10, and 100 becomes 1. So perhaps this in this way this becomes a little bit less messy and easier to put into a calculator and make less mistakes. Like so. Maybe even we could open the brackets and see what happens. Going to be 50r minus 49 on the numerator and 10r minus 9 in the denominator, but that doesn't really matter. When you plug it in all into the calculator, you're supposed to get the same answer. I mean, it again, maybe you reduce the number of errors if you simplify it to the form that it in the end, you know, the simplest possible form should be easier to plug in into the calculator. There's a number of ways this can be still reduced, but since we're about to plug it into a calculator anyway, so I wouldn't bother reducing it too much, because it again takes time at the exam. And so once we obtain some number from this, it's going to, okay, I'm actually curious. I'm going to do it after all with a calculator. 1 second. Okay, so here I plug it into a calculator, this formula. So instead of r, as you can see, I have a 1.04 to power 1/12, which is the same as the 12th root of 1.04. And then I have plugged in that into this formula, which I have. And what I get is 36.5 something. Now, what does it mean? It means that we reach 5,000 euros when at the beginning of 37th. Wait, we were talking about the end. So the end of the month 36 is not yet 5,000. It has to be the end of the month 36 and a half. So if we round it up, because this increments happen in stages, so at the end of month 37 we are above 5,000. At the end of month 36 we're still below 5,000. So that's the answer is 37 in this case. Makes kind of sense because we had that in 24 months we reach 3,000 something, and so it makes sense that when we want to reach 5,000, then it's 37 months, which would then be, if we start from 2022 January, then 36 months would be exactly 3 years plus 1 month, so end of January 2025. Okay, that's about it. In the description of this video, please find a link to my live sessions, which are specifically targeting IB mathematics, preparing IB students for the May exams, which are coming up in no time. So if you're in IB, you're a second year, you're writing your math papers in May, you must join my live sessions. They're almost every day, they're very cheap. Please check them out, and also please just leave comments if you have any questions about what I just did or any other questions about IB mathematics. I am here to answer all of them and help you to get the best grades you possibly can achieve in those exams. Yeah!